So far, in our discussion of neurophysiology, we've really taken kind of a piecemeal approach. And by that, I mean we've looked at a single neuron and looked at parts of it to figure out what's happening. And we've really focused on what's going on from the axon helix and how those electrical propagations in the form of action potentials make it all the way down to the axon terminal, and more recently than what happens at the axon terminal. And in this lecture, we're going to focus on completing the story. So hopefully we'll no longer be looking at a piecemeal approach, but rather a cohesive story by the time we are done with this particular lecture. So when we look at the axon terminal, if that particular cell is right next to another cell, it's probably trying to talk to that other cell. And so you can kind of see that here, where the information is somehow being conveyed into that postsynaptic cell by way of a neurotransmitter. And we've looked at what some of the different neurotransmitters are, and we've looked at the types of receptors that we'll see. And to briefly reiterate, we have learned that it is the receptor type that we see in a postsynaptic cell that will dictate the response of that postsynaptic cell. And there are really two major types: G protein coupled receptors, but then also gated ion channels. So if that gated ion channel allows chloride through, chloride comes into the postsynaptic cell, causing a localized hyperpolarization. If the gated ion channel lets predominantly sodium through, then sodium diffuses into the cell, and that causes a localized depolarization. We refer to these localized changes in the membrane potential from the default minus 70 millivolts position as graded potentials. So these are not action potentials, but that's certainly not at rest. We are getting some deviations. So these are called graded potentials. So graded potentials are localized changes in the membrane potential due to some ion movement. And the word localized is kind of important. Let me explain why. So I'm going to zoom out here momentarily. But first, I want to just point out where we are in this picture. We're looking at a chemical synapse, and we're spending most of our time looking at the fact that the postsynaptic cell is getting the neurotransmitter at the cell body. So one of the things to note is that when we have a gated ion channel that opens as part of our postsynaptic cell response, then the ion flow will be most concentrated right next to that synapse. So in this example, sodium is coming in, right? So this is a depolarization. But the depolarization is going to be the strongest right there. And as that sodium comes in, it will in fact exhibit simple diffusion throughout the cell body. But as it does so, it dissipates. It becomes weaker and weaker and weaker. And therefore, the depolarization that you experience at that point is going to be much weaker than the depolarization right at the synapse. So let's take a look at why this is important. In order to understand the importance of these graded potentials, we have to remember that action potentials will start at the axon helix and then move their way down if a membrane potential of minus 55 millivolts is reached. That's the threshold. So let's consider for a moment that we allow positive charge in right here. And when we take an electrode and we measure the membrane potential at that point, let's say that it's all the way up to minus 10 millivolts. That would be enough to start an action potential if the cell body could do an action potential, but it doesn't. There's no voltage-sensitive gated channels there that permit action potentials. So action potentials do not happen in dendrites, and they do not happen in cell bodies. Okay, so the question is this. is enough of that positive charge preserved by the time some of that sodium makes its way through the cell to ensure that once we get to this point, we are at least at minus 55 millivolts? That's the question. So now we come full circle with our story. So a purpose of these graded potentials is to change the membrane potential in a way that makes it more or less likely for the axon helic to actually start an action potential. And right now, we're just going to focus on the more likely scenario. So we'll just keep this lecture focused on sodium. We'll look at chloride in the next lecture. But for right now, we're just going to look at the depolarization and is it enough? This image from your book addresses that same question. Will it be enough to start action potentials? It's a busy picture, and I think it's probably best addressed to look at independently. So I'm first going to zoom in here a little bit to the one on the left. Here we have a little bit of positive charge, and it seems to be enough that it's just under the minus 40 mark at that point. But we do definitely expect some loss of charge as those positive ions start moving about. So by the time we get to this point in the cell body, you can see that we're right at threshold. But even more dissipation happens. So by the time we reach the axon helic, which is the trigger zone, that graded potential has lost enough strength that it is no longer above the minus 55 threshold, it is below it. So unless you reach that minus 55 millivolts threshold, no action potential is generated. So basically, nothing happens here. And if there's no action potential at the axon helic, no action potential propagation or electrical conduction occurs down the length of the axon. There's nothing that happens. It's just over with. It's like blip, nope, nothing. So nothing happens. But let's say that the initial depolarization was quite a bit stronger, so that we actually exceeded that minus 40 millivolts mark. Yes, there's a little bit of loss, but because we had such a strong graded potential to begin with, we're still at above that minus 55 point. And then by the time we reach here, we're still above minus 55 millivolts. So what's going to happen in this swath of membrane right here is the voltage sensitive gated sodium channels are going to open and start the events of an action potential, which then will automatically generate a series of action potentials that move down the length of the axon to the axon terminal. So this is why the axon helic is referred to as kind of like the trigger zone. It's either green light, red light. There's no in between. You either have enough of a depolarization event in your graded potentials to reach that minus 55 millivolts threshold, and therefore you start action potentials, or your depolarization is too weak and the cell bodies and the dendrites and too much of the charge dissipates that by the time we get to the axon helic, it's not strong enough. There's not enough of a depolarization to trigger an action potential, and so there's no action potentials. So in this example here, this is definitely the green light, and this is the red light. No action potentials occur on the left, where action potentials definitely start going down the length of the axon. So the importance of graded potentials is that they directly influence whether or not the postsynaptic cell will generate its own set of action potentials and electrical conduction down the length of the axon, and therefore continue the signal. That's the point. So I'm going to leave you with this concept now, and we're going to pick up on some nuances and deviations to this idea in the next lecture when we talk about things called summation, excitatory and inhibitory actions. But before I go, I want to leave you with this particular table. Now, if you are in my class, I simply do not ask you to fill in tables. That's not really a thing that I ask you to do on exams. But I like this table because all the information is there in terms of how graded potentials, which occur in the cell body and the dendrites, are totally different than action potentials. Okay, so I'll leave this here. Please pause the video and go over all of the information that's on this table. Make sure it makes sense to you, and then I'll see you in the next lecture.